number. That is, it's conserved, right? Why it is conserved, Ritika, is because if you look at the Hamilton's equations of motion, or Heisenberg equation of motion in this case. So, for instance, if you do now Pz dot, Pz dot is a commutator of the Hamiltonian with Z. But the Hamiltonian does not have any Z. Okay? So, therefore, that term is 0. So, Pz is a constant of motion, which is physically clear because the Lorentz force says that there is no force along the Z axis. The force is only in the xy plane. If there is no force in the Z axis, the motion is exactly like that of a free particle. Similarly, for this particular gauge, you see that the motion along, there is no y dependence either, so Py dot is also equal to 0. So both Py and Pz are what are called constants of motion. They are called good quantum numbers, right? Simply because you just work out the equations of motion. So then, of course, this is gauge dependent. What is not gauge dependent is the equation, or the equations of motion. When you write down the equations of motion, of course, you will get these equations. You can work them out in terms of P, and you have to be careful now that Px and x, of course, do not commute. Remember that there is a commutation property between x and Px, and that's simply equal to IH bar. So, because Pz and Py are good quantum numbers, or they're constants of motion, I can choose my wave function xyz to be such that you have, see, if that constants of motion means it's like free particle motion. Free particle motion will give you plane wave solutions. So it will be I kzz plus I kyy, and the rest of the stuff, of course, will depend on x. So I can choose my wave function in such a way. Is there any question on this? No? All right. So what we have managed to do is to actually disentangle the three-dimensional wave function into a one-dimensional wave function, because now if we plug it into my Schrödinger equation, the Schrödinger equation would look the following. So the system, of course, remember what is the Schrödinger equation? That is H psi is equal to E psi. Okay? And you put this Hamiltonian on the left-hand side. You put this Hamiltonian, operate by px squared, pz squared, py squared, etc. Each of these p's is a, for instance, this is minus IH bar del del x, etc. And when you do del del z, you bring down kz once, if you bring it multiplied by I. When you do it twice, you get 2, bring down 2I kz, so you get minus kz squared. And so net result will give you a one-dimensional Schrödinger equation. So you get, sorry. This is pretty elementary. You'll find it in any book in quantum mechanics. And on the right hand side, you get an energy eigenvalue, which is E minus H bar squared kz squared to n pi over x. This is very physically very easy to understand. And what is my capital X? Capital X defined as H bar kyc divided by EB. So this is definitely has a dimension of a distance. And so that's what you get. Okay. So even if you use the Landau gauge, you'll still have this kz as a free particle motion. So you'll still have this term subtracted from the energy E, where E is this E. because of this Landau gauge, you also have this additional term here. So what does it mean? Do you know what this is called? This is what is called a displaced harmonic oscillator, where you displaced a harmonic oscillator has a center of force, and you have a linear dependence on the force of the distance, right? So the force is linearly dependent, potential is quadratically dependent, but if the center itself is moving, then you have a displaced harmonic oscillator. It's an elementary example in the quantum mechanics that if you have a displaced harmonic oscillator, you can again solve the problem exactly. The wave function will be displaced, but the energy eigenvalue will not change. However, now, the displacement, the center of oscillation of this harmonic oscillator depends on the Ky value. The Ky, of course, takes a continuous set of values, right? It's a momentum eigenvalues. We have a continuous set of eigenvalues. So you have a whole lot of centers. So basically, therefore, you have a whole lot of these are Landau orbits in this two-dimensional plane because of the magnetic field. Okay, so what we are saying is that the magnetic field is going like this. The Lorentz force is making the electrons move in the plane, all right, which is normal to the magnetic field, all right. So anything moving in a plane in like a circle means that you have two coupled simple harmonic oscillators. So actually, if I don't use a Landau gauge, you might simply say, well, things cannot be gauge dependent. So if you use a symmetric gauge, you can see explicitly that you actually have two harmonic oscillator coupled motion in the x and the y directions. Okay? But this is a simpler way of doing it because now you have reduced it to just a single one-dimensional harmonic oscillator. Okay? Except that the energy, so therefore the energy eigenvalues would be identical to what you have done in your first course of quantum mechanics on 1D harmonic oscillator, except now the energy eigenvalues are highly degenerate because you can physically you can choose your center at any point in your two-dimensional plane. That is, you can shift your x and you get the same energy eigenvalue. That's very, very important to get Landau diagrams, which we'll discuss. So let me then write down what the energy eigenvalues are. So everything is so quiet. Is it that you understand it? This is trivial stuff, right? So if you did not have this term, then you simply have a 1D harmonic oscillator, right? So what are the energy eigenvalues of a 1D harmonic oscillator? Let me not write E capital N now. For the 1D harmonic oscillator, the characteristic frequency is of course omega c, which is the cyclotron frequency. This is called the cyclotron frequency, which you have defined somewhere here. Yeah, the cyclotron frequency times J plus half, these are the quantum numbers, plus you add this extra term. This is simply coming from the free particle motion along the z-axis. So you have simply h bar squared. Either you write it as kz squared, but these are all numbers now. These are all a good quantum number. So when J therefore runs from, just as you have 1D harmonic oscillators, J runs from 0, 1, 2, etc.
So it's not completely obvious that to me actually, that the fact that, see, because this mod psi squared should be the same regardless of the gauge.
Yes.
So psi x actually, so you have these, so what it's saying is that you actually shift, you have these strips, and you shift these strips to construct different degenerate wave functions.
Right.
So what is the mapping of that to the circular orbits is not completely clear.
Mapping of?
Because they should be exactly one-to-one mapping.
Absolutely.
Because the wave function is related by a gauge transformation.
Right.
which connects the two gauges. So what I'm saying is that this is like the phi x, which is a strip, and you can shift it by these ky's.
Yes.
But then each one of those things actually has a one-to-one mapping onto a circular orbit.
Precisely. Precisely.
Symmetry gauge. So,
Right.
so it's not quite obvious.
So you have to then do the same exercise for the symmetric gauge.
Okay, because for some reason, if you do psi squared, it turns out to be like a circle or something, is it? Meaning it turns out to be like a circular. You see what I mean? Because not psi squared should be a gauge independent part.
So if I solve for the psi, so psi would have plane wave solutions along Z, and you only have Hermite polynomials. So let me actually write down what since you are asking me.
Some kind of a modulated thing around the x, Hermite polynomials.
Yes.
Okay.
So let me actually tell you what those, since you asked me.
Gaussian, for instance, the ground state.
Pakka.
So now the thing is, so what I don't know if I'm able to say it properly.
Now let me just write it down and then maybe I understand your question a little better. So 5 turns out to be, okay, that's why I think I had an n here because it's called the nth band. So phi nx of x is all this normalization factor, 1 square root I 2 to the n factorial L. L is the magnetic length. The Hermite polynomial of order capital N now is a displaced Hermite polynomials over L. So I'll define L momentarily. So L is what is called the magnetic length. Times exponential, these are your Gaussian functions. Okay, and Hermite polynomials, as you know, are defined as Hn of x is minus 1 to the power n, a to the power minus x squared. The nth derivative of an exponential function. So now what goes?
So the question was, so that's okay.
Let's say in the book by Wang in statistical mechanics, because there's also a Stacklet problem. See, when you did not have the magnetic field, B equal to 0, all you had is a continuum of states. Like free particle states. When you go to B not equal to 0, this rate is probably not very visible. So yes, the more important thing for B not equal to 0. For B not equal to 0, you have discrete levels. They're called the Landau levels, right? So you have discrete levels. Now, so they're exactly like harmonic oscillator levels. However, because I have the freedom to choose where the center of motion of this oscillator is, which actually can take any possible value because of the possible values of ky, these levels are highly degenerate. So the picture that you will find in Wang's book is that, so when you try to calculate this degeneracy, you find that the degeneracy actually is independent of the level concerned. So basically what is happening is that a bunch of free particle-like states collapse into a single level like this. So we'll calculate this degeneracy because it's important to calculate it in order to get the Landau diamagnetism. So this degeneracy is happening because I can have the center of this Landau orbits or cyclotron orbits anywhere in my two-dimensional, for instance, in the graphene plane, right? In two-dimensional plane, or in the electron gas problem, a free electron gas problem in a box. I can have the center anywhere, and having the center anywhere means that I'm changing the wave function, right? The wave function changes on the physical location, but the energy eigenvalue does not change, and that's the meaning of degeneracy. Okay? It's a highly degenerate problem. We'll will show very soon that the degeneracy actually depends on the area of the sheet or the plane that you are looking at. So the area can be very large in the so-called thermodynamic limit. For example, it is extremely large. Even for graphene, you can see that it's a graphene sheet. So the area can be very large. So the degeneracy becomes very large. Degeneracy is proportional to the area, proportional also to the magnetic field, you'll find out. And therefore, by raising the strength of the magnetic field, in these matters we have experts here like Dr. Gonza, that you can have very large degeneracy. So you can pump in lots and lots of electrons in the lower levels. So quantum Hall effect and fractional quantum Hall effect, etc., are high magnetic field phenomenon and at very low temperature, so that you occupy only the lowest lambda levels, and because of this high degeneracy. We'll see that. Bhaskash, you want to make any comment on this? Are you doing this experiment?
No, not yet.
This magnetic length that I was talking about, for we have colleagues here who know much more than me in this subject, but if you have, for instance, B equal to 1 Tesla, do chemists use Tesla or Gauss? Tesla. So for B equals 1 Tesla, the length, the magnetic length is of the order of 25 nanometer. Okay. So this is something you will find in Wang. You want to calculate what is the degeneracy. And I will give you a simple-minded calculation. So what is a physical picture? I have cyclotron motion. The electron goes in a circle. The circle roughly has a radius. The only length scale that is there is the magnetic length. Not quite. You see a factor of square root 2 here. So suppose I now want to calculate what is the degeneracy. There are many books which do this. Actually, I should promote a book of my colleague. It's an Indian publication. Well, actually, it's World Scientific now. It's by JKB, Jayan Bhattacharya. Excellent book in statistical mechanics. And it does the Landau problem in detail. So physically what is happening is that each of these orbits has some kind of an area, right? What is the area of an orbit? Pi times the radius squared. So it will be the only length scale that is there is the magnetic length. So it's pi times L squared. Then you ask the question, how many such circles I can fit in an area of A, right? Of course, circles don't fit in a planar sheet, so you'll have a factor missing. So it turns out, and this is something that you can see in JKB or Wang, okay? The degeneracy eta is actually A divided by pi L squared, and this is factor 2, which is coming in because, I mean, this is an exact answer. I gave you a simple-minded answer. A simple-minded way of getting at it is you ask the question, how many such Landau orbits you can fit in an area A. That's the degeneracy. So what is L squared down there? Remember, I had given an expression for L somewhere, which I actually did not, right?
You have.
Huh?
You have.
I haven't yet. So the magnetic length is defined. Sorry. Have it here. I don't want to miss any factor. So when you have notes, you are tempted to look at your notes. Otherwise, you remember everything. You're forced to remember. So, yeah, here it is. The magnetic length L is equal to square root HC divided by EB. So you can also write this as therefore A divided by 2 pi. I now have 1 over L squared. So I get PV over 8 pi.